Welcome to the program documentation on prime number check. In this presentation, we'll explore a Java program that determines whether a given number is prime. The focus is on using a user-defined function for modularity, along with an efficient algorithm that uses square root logic for faster computation. Let's begin our journey into structured coding and smart number analysis. In this task, we are asked to write a Java program that takes a number as input and checks if it is prime. We must use a user-defined function called check, which takes an integer parameter and returns 1 if the number is prime, or 0 if it's not. This promotes modular programming and separates logic from user interaction. Let's understand the step-by-step algorithm for checking whether a number is prime. First, we start the program and define a function named check that takes an integer n as input. If n is less than or equal to 1, we immediately return 0 because it's not a prime number. Then, we loop from 2 up to the square root of n. If any number in that range divides n exactly, it means n is not prime, so we return 0. If no such divisor is found, the number is prime and we return 1. In the main method, we take user input, parse it to the check function, and display the appropriate result. Finally, the program ends. This slide focuses on the user-defined function named check, which is responsible for determining if a number is prime. The function is declared as static int check int n. Let's break that down. Static means this method belongs to the class, not to any object. In Java, the main method is static, so to call check directly from main, it also needs to be static. This avoids the need to create an object of the class to access it. Int is the return type of the function. It returns 1 if the number is prime, and 0 if it's not. Check int n means the function accepts an integer input n. Inside the function, the first condition checks if n is less than or equal to 1. Since 0, 1, and negative numbers are not prime, we return 0 right away. Then we use a loop that starts from 2 and goes up to the square root of n. We use math.sqrtn to reduce the number of checks, improving efficiency, because if a number has a factor larger than its square root, it must also have a smaller factor. Within the loop, if n%i equals 0, it means n is divisible by I, so it's not prime. We return 0. If the loop finishes without finding any divisors, we return 1, meaning the number is prime. This method is concise, fast, and follows good programming practices with separation of logic into a reusable function. This slide highlights the main method, where user interaction takes place. First, we create a scanner object named sc to read input from the user. The program prompts the user to enter a number, and reads the input into the variable num. Then, the program calls the check function with num as the argument. If the return value is 1, it means the number is prime, so the program prints, num is a prime number. Otherwise, it prints, num is not a prime number. Finally, we close the scanner using sc.close to release system resources. This structure separates input, logic, and output clearly, making the code easy to read, maintain, and test. In this slide you will get the full program link which you can execute the entire program. Also, program link is available in the description box. This slide presents the variable description table, which summarizes all key variables used in the program. First, n is the input to our check function. It's an integer that we want to test for primality. Then, I is a loop variable used to test divisibility from 2 up to the square root of n. Num stores the number entered by the user from the console. It is passed to the check function for evaluation. Finally, sc is our scanner object used to read user input. This table helps clarify the purpose and data type of each variable, making the program easier to understand, debug, and document. This slide shows two sample outputs of the program to demonstrate how it works. In the first case, the user enters the number 29. Since 29 is a prime number, the program correctly outputs 29 is a prime number. In the second case, the user enters the number 20. Since 20 is divisible by 2, the function identifies it as not prime, and the output is 20 is not a prime number. These examples confirm that the program is functioning correctly for both prime and non-prime inputs. Let's quickly recap what we've learned in this program. We used a user-defined function called check to determine whether a number is prime. To optimize the logic, we only checked up to the square root of the number, a well-known efficiency trick. By declaring the function as static, we allowed it to be called directly from the main method without needing to create an object. The program follows a clean structure with separate sections for logic and input/output, making it modular and easy to debug. We also validated inputs by checking for numbers less than or equal to 1 and documented our work with a clear algorithm, variable table, and sample outputs. Thanks for watching. Documentation containing question, algorithm, Java program, variable description table, VDT, sample output is also available in description box of this video. Don't forget to subscribe if you are using this for your school or college projects. Happy learning!